motion of a falling object for Lab 2 for physics. So the main goal for this was to understand the object, the falling object, the motion of it, and the forces acting on it and stuff. So I'm going to make two different computational models, one including drag and one discluding drag. And then I'll explain what the terminal velocity of a falling object is. A little spoiler alert with the results is that the computational model with drag is going to represent the motion and the acceleration much better than the computational model without, because it's just how force works. And so some important concepts. This is the gravity equation for Earth. So little g will end up being 9.8 meters per second, which is acceleration due to gravity. This is the equation for drag, the force for that. And so basically what drag is you can see in this little picture that the body, the ball in this case, is released, and the only force on it acting then is is gravity, and whatever is holding it up. And then as the ball falls, it gains more drag, and then the drag force increases. And basically what terminal velocity is when the drag force and the gravity force are the same, and that is like the max speed it can go when it is falling. So here is a picture of a little snapshot of what I did with this. This was my measuring stick. Basically, it was 27 inches, which is about 0.7 meters. So put that into this, and it was 0.33 seconds, which is pretty lucky for it to hit the ground. And so this is the acceleration, or the distance versus time graph for the ball falling and me clicking on it. So here's the computational model for gravity. So for the code, I had 0.333 seconds for the time, and then this was the equation that is for the net force. So how much force is acting on it, and so that is this model. And so this is just the velocity update and the position update formulas. Delta t is the time update equation. And then this is the computational model for gravity and drag. Same thing, but I added the drag formula to it. And so add those together and you get your forces acting on it at a specific moment. Same velocity update, position update formula. And so the drag will make it accelerate slower, which in turn causes it to fall less over less time, or fall less over the same amount of time. So here's comparing them. Blue is the observed. As you can see, there's blemishes and bumps and stuff from me clicking on it wrong, or just visual and human errors. And then the red one is without gravity, and obviously it went further because there's less forces acting on it. And I'm really happy with how I did it and how the computational model worked, because it ended up pretty much in the same place. Didn't start exactly the same because of human error, but pretty close. And so I'm pretty pleased with that. And as you can see, the red, which is the without gravity, and the yellow, which is with gravity, start the same, and you can see them start to come apart as drag increases and the gravity is able to take away without it. That's pretty much it for that. And then this shows the velocity charts. I had to increase the time to 1 second to actually show like the velocity chart instead of just this little snippet of it, which we can't really see how the terminal velocity goes towards asymptote. And so that is this without, like, starting at 0 meters per second. This is starting at -1 meters per second. And you can see that it approaches the asymptote a lot quicker because it's already at a speed, so it's like you're saving 0.1 seconds. So this is pretty much just 0.1 seconds further along with velocity. And so this is basically the what if it was thrown. And yeah, that's about it. Thank you for watching my video.